right, well, it's good to see you all. Should we go ahead and get started?
I suggest yes.
Do we have any announcements? Would anyone like to make any announcements? Stephanie just defended her PhD. So.
I was about to say we should all congratulate Stephanie.
Thank you.
I'd also like to announce Josh was our new chair for the early career program. So thank you for stepping up.
My pleasure.
And we've been forming committees and discussing various roles for the group, which is great. So today we're going to have two presentations from graduate students in CRESP. And so I think we should go ahead and get started. I think both of them are presentations based on waste management conference. And did you say, Zhiliang, you're going first? Is that right? Or
yeah, I'll go first.
Yeah, yes, Zhiliang's a postdoc also.
Oh, postdoc.
Yeah, I'm a postdoc. Yeah.
Great. Thanks for thanks for
updating
me on that.
Should I just get started?
Please go ahead. Yes.
Okay. All right, I guess you can see my slides, right? So yeah, so hi everyone, I'm Zhiliang Chen, a postdoctor in Dr. David Carson's research group, and today I'd like to share some of our work regarding this leaching and agent assessment of the cast stone waste form under field scenario. So this is the presentation I've given for the waste management conference. So today I'd like to share it one more time, so that I hope you will find it interesting and probably helpful to you. So my research object is for the cast stone, which is a cementitious material that has been developed for the treatment of the radioactive waste at the Hanford site. But during its service life of over 1,000 years, it will be in contact with the infiltration water, and so the contaminants in it, like the technetium or iodine, will release into the environment. So our project goal is to develop models based on some experiment results to more accurately estimate the contaminants released from the ground waste form under field conditions. And also the impact of the agent processes like the drying, oxidation, and carbonation on the release rate of the contaminants will also be estimated in this work. So specifically, we have 3 different objectives. The first is to develop a geochemical speciation model to account for the solubility of the constituents in the port of the cast stone, and then to develop an agent model to estimate the oxidation and carbonation depths along with the agent times of the cast stone under field conditions. And finally, by combining the geochemical speciation model and the agent model, we will further develop a reactive mass transfer model to assess the long-term leaching of the constituents. I'm sorry?
I think somebody was not muted. Go ahead, Zhiliang.
All right, yeah. So yeah, finally, by combining the geochemical speciation model and the agent model, we will develop a reactive mass transfer model to assess the long-term leaching of the contaminants. So the long-term performance has already been assessed in a report under the IDF at the Hanford site. So here I'd like to firstly show some differences in the modeling approaches between the report and in this work. So the modeling scenario in the report is for the ground liquid secondary waste, while the modeling scenario in this work is for the grounded primary low activity waste containing polypropylene bags. And for the agent of the cast stone in the report, the cast stone is assumed either in reduced form or in completely oxidized form, and the carbonation was not considered in the report, and also the agent rates was not estimated. While in this work, we developed an agent model to estimate oxidation and the carbonation depths along with the agent times. And also the agent rates was derived based on some experimental results. And for the leaching of the cast stone in the report, the impact of the oxidation and carbonation on the physical retention ability of the cast stone was not considered. And also the distribution coefficient, or the KD value of the contaminants, was estimated based on some relevant studies, and also the observed diffusion coefficient from the EPA method 2015 test results. And also the leaching during the pre-chloride period was not considered in the report. In this work, we estimated the extent of the oxidation and the carbonation, and also their impact on the contaminants release rate. And also we developed a geochemical speciation model together with a reactive mass transfer model to estimate the contaminants release rate. And also the developed model have been verified against experiment data. And this is a framework for the models development starting from the agent experiments. The agent sample was then used to conduct different leaching tests, including the pH-dependent leaching test and the monolithic diffusion leaching test. And the test results are used to develop different models, including the geochemical speciation model, the monolithic diffusion model, the drying model, the agent model, and finally the reactive mass transfer model. So with the input of the hydrological modeling results of the IDF and the estimated long-term oxidation and carbonation depths, we can use this reactive mass transfer model to estimate the long-term contaminants released from the Keystone under the IDF disposal scenario. And today's presentation will be mainly focused on the highlighted lower part. So this is just a brief overview of the agent and leaching experiments. For the agent of the Keystone, the samples were put into containers and then maintained under different aging conditions for different periods of time. And the agent sample were then used for the leaching characterizations. And based on the experimental results, different models have been developed. And more details regarding the model development can be found in these several papers that we have published. And specifically for the agent model, we firstly developed a drying model to describe the model moisture transport between the Keystone and the environment. And then we further incorporated the diffusion of oxygen and CO2 into the drying model to develop an agent model. And finally, by extrapolating the agent model with the input of the agent conditions on the field scenario, the agent model can be used to estimate the long-term oxidation and carbonation depths. And here are some comparisons of the oxidation and carbonation depths from experiments and from models. So at the top are the comparison for the oxidation depths, and the results at the bottom are the comparisons for the carbonation depths. So as you can see, the modeling results agrees pretty well with the experimental results. So that means the agent model that we have developed is well capable of describing the agent processes, including oxidation and carbonation under different agent conditions. So yeah, now we have developed a representative agent model and also a geochemical speciation model. But to estimate the long-term performance of the Keystone under field conditions, we still need the agent and leaching conditions of the Keystone under field scenario. And for the IDF at the Hanford site, the Keystone will generally go through a pre-chloride period for 50 years and a post-chloride period for 1,000 years. And under the pre-chloride scenario, the agent conditions is assumed as an ambient air with low relative humidity of around 54%. And the infiltration rate is estimated as 12 millimeter per year because at this stage, there's no cover at the top of the facility to prevent the infiltration. And under the post-chloride scenario, the agent condition will be changed from the ambient air to the soil gas with higher concentration of CO2 and also higher agent relative humidity of around 100%. And specifically for the early post-chloride scenario, the infiltration rate is only 0.5 millimeter per year because at this stage, there is a functional cover at the top of the facility to prevent the infiltration. But for the late post-chloride scenario, the infiltration rate will be increased from 0.5 to 3.5 millimeter per year because of the degradation of the cover. So with above agent time frames and the agent conditions, we can use the agent model to estimate the variation of the oxidation carbonation depths along with the agent times. At the bottom in this table, I summarize the oxidation and carbonation depths at the end of the pre-chloride and the post-chloride period. So as you can see, a large fraction of the oxidation and carbonation happened during this pre-closure period with relatively short period of time, with only 50 years. The major reason for that is under this pre-closure scenario, the agent relative humidity is only 54%, which is lower than the agent relative humidity under the post-closure scenario. So lower agent relative humidity will facilitate the moisture transport out of the castone and also facilitate the ingress of the oxygen CO2 into the castone. So the agent rates under pre-closure period is much faster compared to the post-closure scenario. And next, we will look more into the impact of the oxidation and carbonation on the chemical speciation of technetium and the iodine. And the information can be obtained from this predominance diagram. So this is the predominance diagram for the technetium. It mainly consists of 3 different regions, like the light green region indicates technetium has highly soluble free ions. And the dark red and dark green region indicates technetium as insoluble form because of either adsorption or precipitation as minerals. So, the redox state of the original castone, as indicated by this green square dot, is in the region of insoluble technetium. So that means the redox states of the original castone is capable of stabilizing technetium. However, for the oxidized castone, the redox states indicated by this green square dot, or not green, blue square dot and the red square dot are in the region of highly soluble technetium. So that means the oxidation of the castone will greatly increase the mobility of the technetium. And for the iodine, we in fact investigated 2 different systems, and on the left is the results for the system without the iodine getter, and on the right are the results for the system with iodine getter. The getter is assumed as a silver-containing compound because the silver will precipitate together with iodine to stabilize the iodine. So we have some key observations here. Firstly, the redox state for the original castone, as you can see, indicated by this green square dot, are in the region of highly soluble iodine for both 2 systems. So that means the redox state of the original castone is unfavorable for iodine stabilization, even for the system with the getter added. So the getter may not be effective within castone because of the reducing conditions there. But if we take a look at this round open square dot, round open dots, they are in the region of insoluble iodine for this system with the getter. So that means the getter may be effective if it's distributed in the backfill or within the IDF liner because of the oxic or less reducing conditions there. And also, if we take a look at this red square dot, it's also in the region of insoluble iodine. And this is the redox state for the oxidized and carbonated castone. So that means the oxidation and carbonation is actually beneficial for the stabilization of the iodine for the system with the getter. And to estimate the contaminant release, the water flow rate is also important basis. So Nick and Dr. Benson has helped us conduct this hydrological modeling to estimate the water fluxes around and through the castone. And here are the modeling results for castone on the pre-closure scenario. And these are the modeling results. These are the hydrologic modeling results of the castone on the post-closure scenario. So specifically for this post-closure scenario, because of the existence of the cover at the top of this facility, the pore water in the backfill will be spatially redistributed. So that means some blocks may be in wet condition, like these blocks, and some will be in medium condition, and some will be like in dry conditions. So the results at the bottom are example for the median case, and the contaminants released for 3 different cases will all be estimated in this work. And based on the output of the hydrological model, we have some key parameters as the input for the leaching model. So as you can see in this table, the big difference between the pre-closure and the post-closure is like the infiltration rate and the corresponding steady state water saturation of the backfill material. and also the water flow rate around the capstone. So the post-closure period is further divided into an early post-closure period and a late post-closure period. And for each period, 3 different cases, including the dry case, medium case, and wet case, are included. And this is an illustration of the leaching conceptual model. So as you can see in Figure 8, the capstone block is surrounded by the backfill material, and because of the hydraulic conductivity in the backfill material is about 6 orders of magnitude higher than that in the capstone. So we assume the infiltration water is primarily flowing through the backfill material, and during the flow of the water, the contaminants will diffuse from the capstone into the port of the backfill materials. And by taking a half court of this unit, we further develop a reactive mass transfer model as shown in Figure C at the bottom. So in this figure, you can see on the left is the capstone monolith, and on the right is the backfill material with the flow of the infiltration water. And during the flow of this water, contaminants diffuses from the capstone monolith into this backfill material. And for conservative assumption, the polypropylene bag around the capstone blocks is assumed not to act as a barrier for contaminants release. And for the leaching modeling cases, we use different capstone materials and different refresh schemes of the pore water in backfill to conduct sensitivity tests. So specifically, we have 3 different capstone materials, including the original capstone, the oxidized capstone, and also the oxidized and carbonated capstone. And each capstone material is in different water saturation conditions, like including the dry case, medium case, and the wet case. And here we have the modeling results regarding the fractional cumulative release of the technetium. So the results on the left is the release from the original capstone, and the results in the middle is the release from the oxidized capstone. And on the right are the results for the oxidized and carbonated capstone. So the top 3 figures are the results of the total release, and the bottom 3 figures are the results of the release to the vital zone. So the release to the vital zone is derived by subtracting the release of the first 150 years from the total release, because the release of the first 150 years is assumed to be completely collected by the leachate collection system sump at the bottom of the facility. So in each figure, you can see 3 different lines indicating the modeling results for the dry case, medium case, and wet case. So if we take a look at the total release from the original capstone after 1,050 years, we can see that the total release is less than 1%, so which indicates good retention ability of the capstone for the technetium. But we will also notice that after the oxidation or the carbonation of the capstone, the release rate has been dramatically increased. And this is the results for iodine for system without the iodine getter. So iodine is different from the technetium because the solubility of the iodine in the capstone is much higher. So you can see the release from the original capstone after 1,050 years is as high as around 35%, which is much higher compared to the release of the technetium. And also the oxidation and the carbonation will further increase the release rate by a factor of around 2. And finally, these are the modeling results for the iodine for system with the iodine getter. So the getter in the original capstone barely shows any effect on the stabilization of the iodine because we didn't observe the reduction of the release like from the original capstone. But if we take a look at the results on the right, we can see a reduction of the release. So that means the oxidation and carbonation is actually beneficial for iodine stabilization for the system with the getter. And here I summarize the release of the technetium and iodine for different cases. For the technetium, you can see that the release from the original capstone is lower, like less than 1%, but oxidation and carbonation increases the release by a lot. And the iodine in the system without the getter is the release is much higher compared to the technetium. And also you can see that oxidation and carbonation will further increase the release rate. But for the iodine in the system with getter, we will notice like the results at the bottom, the oxidation and the carbonation is actually beneficial for the iodine stabilization, and that can reduce the release rate by a lot. And this is because the oxidation and carbonation of the castone will change the redox state of the castone to be beneficial for iodine stabilization, and this is this result is consistent with our previous observation from the predominance diagram. Yeah, and finally, we have some takeaway messages here. A large fraction of the agent, including the oxidation and carbonation and contaminant release, occurs during the pre-closure period, with a relatively short period of time of 50 years. And during this period of time, the IDF liner and the leachate collection system are functional. And also the combined oxidation and carbonation are detrimental for technetium retention, but are beneficial for iodine stabilization in the system with gather. And finally, the gather may not be effective within the castone because of the reducing conditions there, but it may be effective if it's distributed in the backfill or in the IDF liner because of the oxic or less reducing conditions there. Yeah, and finally, I'd like to acknowledge the support from the US DOE Office of Environmental Management and Office of River Protection. Thank you all for your attention and time. Thank you.
Thank you. Let's we have time to take some questions.
Mm-hmm. Sure.
If you want to speak up or if you want to put it in the chat.
I have a question.
Mm-hmm.
First of all, great presentation, Zhiliang. I think that's really awesome work. The question I have is related to the 1,000-year projections that you showed at the end. You had mentioned that you were modeling a pre-closure scenario up to 50 years, but
Yep.
It seems like there's significant repeatability of some sort of change in the status there at 600 years. What would you describe as happening there?
You mean?
Yeah, it seems across a lot of your graphs, the total release and the release to the vadose zone starts to change in projection at around 600 years. Do you know why in the modeling it's showing that?
Oh, you mean around this point, 600 years?
Yeah.
Yeah, because here we have 3 different leaching scenarios. Firstly, maybe here is more clear.
Okay.
Firstly, we have a pre-closure period for 50 years, and then 500 years of early post-closure, and finally 500 years of late post-closure. And for each period of time, this is the the water flow rate around the castone. So the water flow rate for the pre-closure is the same, keep constant, but the flow rate for the early post-closure and the late post-closure are different for different cases. This is the dry case with the lowest flow rate, and medium in the middle, and the wet case with highest flow rate. So yeah, at the time around 600 years, you can see that the flow rate will be changed by a lot, so that will impact the release rate. So that's why you observe these changes at this time point.
Oh, great, thanks. I think I just missed that change, that time change. Focused
no,
on the
it's
50
a lot
years.
of information.
Yeah.
Good call. Other questions? I was wondering what happens to the leachate when you in the early period. What it's collected. Do you know what is done with that?
You mean this early stage?
The first 50 years, you said it's collected.
Yeah, because the liner is still functional, and they have a sump at the bottom of the facility to collect the leachate. So we assume there's no release of the contaminants into the vadose zone. So
yeah. Is it put back? Would it be put back into grout? Do you think? Is that way to do you know?
You mean the treatment for the collected leachate?
Yeah.
I don't know. Probably
I believe it goes to ETF. I think it goes to the effluent treatment facility. I don't think they try to put that back in the tank farm.
Yes, might recycle.
It would be pretty dilute, and I don't think that they would put that back in the tank farm. they have treatment facilities that they're building for, it's called the effluent treatment facility that goes into the solids facility, the water part. So they treat it through ETF.
Was there another question? I think when I started talking, someone else started talking.
Yes. Hi, Shirley. Thank you for the talk. I had a quick question. It was earlier in your presentation. I think it was something about like predominance of technetium or something like that. Yes, you had these plots. What is the y-axis? I don't know. You may have mentioned this. I just didn't catch it. I had trouble.
The y is the PE value.
What is the PE?
It's like the activity of the electron in the system.
Okay.
The little p like negative log, like pH. But
Yes.
the electrons, not the hydronium ions.
Mhm.
Okay, thank you. I was just, I didn't realize what that was when you were
So
presenting.
this is similar to a Porbet diagram where you'd have an EHPH. And so it's kind of the redox state on
Yeah.
the Y.
Okay. Thank you.
Is there a last question, maybe? Okay, let's go to our second presentation.
Thank you.
from U10.
Can you see my screen?
Yes,
And voice sounds good.
yes, good, go
Okay.
ahead.
Hello, everyone. Oh, yes. Just give me 1 second. Should minimize. Oh, hello, everyone. It's my honor to give a presentation here. My name is Yu Tan, a PhD student from University of Wisconsin Medicine. My topic today is the interaction between geosynthetic liner and concrete in low-level radioactive waste disposal facilities. As I introduced last time, those disposal units were built to permanent disposal the low-level radioactive waste. And those are huge units built by concrete, and they will mix the low-level radioactive waste with cementitious material and pound those material into the disposal unit for permanent disposal of the waste. And at the bottom, I have a lining system to intercept the leachate. So today I'm going to talk a little bit about the lining system in the disposal unit. So this graph is the drawing of the bottom of the disposal unit. So at the very bottom, we have the HDP. We have a lining system containing a layer of HDPE and the GCl and the sandwiched by 2 layers of mud. So HDPE is a typical plastic. It's usually impermeable, and GCl is geosynthetic liner. It's usually used as hydraulic barrier in the lining system, and there are 2 layers of mud. Mud is typical concrete. So in the right figure, this 3 figure here, this 3 figure, excuse me, this 3 figure picture here illustrate how we construct the lining system in the field. First, they construct the lower mud and then put GCl and geomembrane at the top of mud. And then they pour concrete at the top of HDPE to form the up mud. So in the lining system, we use GCl as a hydraulic barrier because so GCl is always used as hydraulic barrier in landfills. Our experience in landfill told us that if the GCl is hydrated in dilute solution, it becomes very impermeable, so it can work as hydraulic barrier to intercept the leachate. But if the GCl is hydrated in calcium-rich environment, the GCl will yield a very high hydroconductivity. It is not able to work as hydraulic barrier. So in this lining system, we have a GCl sandwiched by 2 layers of mud or a typical concrete. So as we know that concrete is calcium-rich environment, it's calcium-rich material, so it may provide a lot of calcium in their pore water. So it may affect the performance of GCl. So the objective of this study is to evaluate how significant are those effects that the concrete may affect the hydroconductivity and the performance of GCL. Before we go to our test, let's take a close look at of GCL. So what is GCL? This is the typical cross-section of GCL, geosynthetic liner. It's usually containing a granular bentonite. This part and sandwiched by two layers of geotextile. So this granular bentonite is usually sodium bentonite. When it's hydrated with dilute solution, it will form this gel structure at the bottom. You can see that it's pretty unpermeable. But if the granular bentonite is hydrated in calcium-rich solutions, the bentonite granule does not swell. So you can image that if we pour water at the top and flow through the GCL, if the granular bentonite is not swelling like this sand particle, and the solution will flow through the space between those granular bentonite and yield high hydroconductivity. So it's not able to work as hydraulic barrier. So as we mentioned, that the key factors for the performance of GCL is the transform of the granular bentonite to the gel structure. So it depends on the swelling of bentonite. So we usually use those swell index tests to evaluate the swelling of bentonite and also as an indicator for the hydroconductivity of GCL. So for the swell index test, we usually have this graduated cylinder, and we pre-fill the solution into the cylinder. And so the solution is what we would like to evaluate. And we have 2 grams of dry bentonite. We graduate those bentonite into the cylinder and let the bentonite swell. And finally, when it reach equilibrium, we record the volume of the bentonite at the bottom. This is the maximal volume that the bentonite can reach in the specific solutions. So this is and then we report those volume of bentonite as swell index. It indicates the swelling capability of the bentonite. So in this column, if we use the sodium chloride in the solution and run those tests with sodium bentonite, it will generate high swelling. Swell index means the high swelling, and it will yield very low hydraulic conductivity, 10⁻⁻11. But if we test the same bentonite, but we use the calcium chloride solution, it will develop a low swell index and yield high hydraulic conductivity. So it becomes permeable. It's not able to contain the leachate. And there is usually our experience that usually have a transition zone here. So if the swell index is higher than 50, it should be the hydroconductivity of the GCL should be low. It should work pretty well. But if the swell index is lower than 50, we may got a problem because the hydroconductivity is about 10⁻⁷, hundreds times higher than we expected. So this is our test. We set up the column test in our lab to simulate the lining system in the field. First, we got the lower magnet at the bottom and put GCL at the top of lower magnet and a layer of HDPE at the top of GCL, and we pour concrete at the top of HDPE geomembrane to simulate the lining system in the field. And also, as we concerned that the GCL is pretty thin, only 1 centimeter, we would like to learn more about what happens in the cross section of the GCL. So we create the 4 centimeter thicker GCL in our lab. So we call this a thicker GCL scenario. The other condition is the same with the actual condition that we set. And finally, when our hypothesis is that the interaction between the GCL and the lower magnet, because the HDPE geomembrane will cut off the interaction between the GCL and the upper magnet. So we take off the upper magnet and take off the geomembrane and pound water at the top to accelerate the effect. So this is the worst case in our condition. We call it saturated condition with thicker GCL. So this is our result. This is our result. First, so the we believe that the GC will absorb water from the concrete to hydrate. If the water in concrete is calcium rich, it will affect the swelling and hydraulic conductivity of the GCL. So first we measure the water content of the GCL after 300 days interaction. So we just set up a column, let them set for 300 days, and take the sample out and measure the water content. The water content of the actual in the actual GCL is the same with the fresh GCL. It didn't happen too much hydration. So this is the figure of the actual GCL. It still have some transformation, but we still found that there are a crack between those bentonite. So if the bentonite can swelling, it can heal those crack. It can become unpermeable. If it cannot swelling, we can image that the water can flow through those crack and yield high hydroconductivity. And for the thicker GCL, the water content of the GCL increased a little bit compared to the fresh GCL. And for the saturated condition, we put water at the top to make the thicker GCL saturated. So the water content is high, and this is the figure of the GCL after 300 days interaction. You can find that it formed those gel structure. It should be impermeable. And then we measure the swell index and hydroconductivity of the GCL after 300 days interaction. For the real cases, for the actual conditions that we test the real GCL, and the swell index is also pretty close to the fresh GCL. And for the thicker GCL, the swell index decreased a little bit. And for the saturated GCL, this is the worst case in our study. The swell index decreased a little bit more. And this result is consistent with our hydroconductivity test. So for the actual condition, the hydroconductivity of GCL is comparable with the fresh GCL, 10⁻11, but yeah, 2 times, 1 or 2 times 10⁻11. When we go to the thicker GCL, the swell index decreased a little bit, so hydroconductivity increased a little bit. And for the saturated GCL, this is the worst case in our study. The hydroconductivity increase present the highest increase or the highest hydroconductivity. But the increase only 3 times. This is not a very high increase in hydroconductivity. It means that after 300 days interaction, the hydroconductivity of the GCL is still pretty low. It is at a range of 10⁻11. So we didn't find significant effect of the effect of concrete to GCL is not quite significant. And we take a close look at those thicker GCL. We slice those thicker GCL into 3 layers at the top and middle, at the bottom, at the bottom. So the bottom is directly contact with the concrete. And we didn't find much significant differences between the top layer, middle layer, and bottom layer in the saturated condition and also in the thick condition. It means that the reaction happens equilibrium in the cross section of the thicker GCL. So we still need to, the previous slides present the results of the react for 300 days. So we still need to learn more. We still want to learn more about the time effect. So how time may affect the interaction between the concrete and GCL. So to study this topic, we also set up a column in our lab and let them react for only 40 days. And we take the sample out and measure the swell index and hydroconductivity and compare to the fresh GCL. So comparing to the fresh GCL after 40 days reaction, the swell index decreased a little bit. And after react for 300 days, the swell index decreased a little bit more. This is consistent with our hydroconductivity result. So after 40 days interaction, the hydroconductivity increased a little bit compared to the fresh GCL, and increased a little bit more comparing to the after 300 days interaction. So right now we only study for 300 days, about 1 year, but but the lining system or the disposal unit is supposed to solve for 1,000 years. So what we can do to make a prediction or to estimate the performance of the liner in the disposal facilities. One thing that we can do that we are running more tests in our lab, more column tests in our lab to let them set for a longer time. And we can take the sample out at 1 year, 4 year, and 8 year, and measure the swell index and hydroconductivity to get a trend to add more points in those two graphs and get a trend we can estimate how it may happen in the future. But the longest time that we can do is depends on when I will graduate. I would not spend more than eight years in those tests for my PhD. So it's still limited. So follow the Nick's suggestion. One thing we can do that our hypothesis is that the interaction between the concrete and the bentonite depends on the cation change between the concrete and the bentonite. So we can wash the cation in the concrete out to get the pure water in the concrete and run swell index test. So this is what I did in the last weeks. So I just mixed the water and concrete at a 1.3 ratio and shake it and finally filter the water to get the water to represent the pure water in concrete and run swell index test with the fresh bentonite. And we found that the swell index test in the kind of pure water in concrete is still comparable with the swell index after 300 days interaction in the column test. It means that in the saturated condition, the column test may have reached equilibrium. The interaction between the concrete and the GCL may have reached equilibrium. So if we run a longer time for the column test, we may got a flat train. We may got a flat tile at the end. So our results are favorable that the GCL works pretty well based on our result for now. So this is the conclusions. First, the contact with magmat do have some effect on GCL. It affects the swelling index and it decreases swell index and increases the hydroconductivity of GCL. And the saturated condition accelerates the interaction between GCL and magmat. And the smallest change happens on actual conditions, so it's favorable that our disposal facilities should work pretty well. But for the over longer time scale, we still need to evaluate because our mix the concrete and the water to create the solution to represent the pure water in concrete is still not quite accurate. So we need to appreciate our sponsor and all those quiz and all those companies provide free material to this study. Thank you.
Thank you. Next
Question?
question.
Yeah.
So just to think about the kind of larger context, what is on top of the mat? That how should we be thinking about what is it?
This is also concrete. On top of the mat is also concrete.
And would this be for a solid waste form, or
I think this
tank waste, or what are you
This is saltstone.
This is for saltstone.
Yep,
Yep.
at Savannah River. So low activity waste put in a grouted waste form goes into these. These are approximately 33 million gallon vaults. There are going to be 12 of them. So as you can see, it's a pretty substantial piece of work. So basically the size of a European football stadium. It's a water tank design. It's pretty big, and there will be like 12 of them.
Okay.
And this is the design from, I think, 7 through 12. Yep. So they're pretty large.
right.
They took a water tank design, but the water tank people forgot to tell them that water tanks leak, which is not a good idea when you're putting a waste form in it. So they've had to do some work on sealing them. And then the double base mat layer helps collect the stuff that comes out. So this is very important. And then the Hanford, we're proposing something similar for study at Hanford for their low activity waste. And then the question I asked at Waste Management was the uncertainty in the line that was drawn through the points that he showed earlier. Craig is smiling because poor Craig gets asked by me this every time he presents. But when you're working with performance assessments, you have to start thinking about the uncertainties, especially when projecting forward in time. So it was a very good talk.
So for the uncertainty, we are going to run more replicate tests to add more points on the graph to evaluate, to increase our confidence on the trend that we obtain from the graph. Yeah, that's a good point. Thank you, Kate.
Do you think about doing accelerated lifetime tests, like at a higher temperature, or sometimes, you know, when things are really slow, people do accelerated lifetime tests. Is that something you're thinking about?
Yeah, that's a very good point, but we have not run the test in our lab. So right now we are planning to run some leaching tests to get a more reliable synthetic pore water in concrete and evaluate the effect of the GCL. But for the other effect to accelerate the degradation of concrete or GCL, we have not reached this point for right now.
And you have to remember the acceleration only works if you don't change the mechanisms. So in
Yeah,
glass,
agreed.
you can accelerate temperature up to about 100 degrees C, and then the mechanisms change, so you get useless data after that. Cementitious stuff is even a little more complicated than something like glass, which is considered amorphous, even though it's not. It's quasi-crystalline.
Osmotic swelling of the bentonite is sensitive to temperature as well.
Right.
So you can change the mechanism. Yeah, go ahead.
So I was just gonna say, I had a similar question about the accelerated aging test, although my thoughts are kind of in the pressure area, considering you're gonna have such a heavy load on top of it. Have you done any sort of like induced pressure testing on the mud vats?
Yeah, we didn't. So I think the pressure is also a good point, but we didn't run the pressure test in our lab.
And it's interesting because these things, they have columns to support the weight. The waste form itself does not have to be structurally integral to the design itself. So you actually hold the weight up with columns and other things, including that dirt that you're going to put over it in the future. So the waste form is a little different here than other waste forms. It doesn't have to have structural integrity related to the waste form.
Okay, cool. Thank you.
If you put it in IDF that we were talking about, that Zhiliang was talking about, if you put those in IDF, it actually has to support the weight above it, whereas something like this does not. So it's a little different problem as well. And I did go back and look, Martha, it is going to be in the 200 area ETF because there are multiple pathways before, but the leachate from IDF is supposed to be treated. Nothing's working there now, but the intention is for 200 area effluent treatment facility, not to run it back to the tank farm.
Other questions? All right, thanks to both of our presenters.
Thank you.
I learned a lot. There's a lot to learn about everything going on in CRESP. So good
It's
start.
master's time. We have to do golf claps, right? I used to live there. What am I gonna...
It is master's time. Yes. Okay. Well, thanks everyone. We'll see you all in 2 weeks, and the committee will meet next week.
Yeah, thank you.
Thank you, everybody.
Thank you all.
Thank
Great.
you.